Tonight, we're going to explore one of the deepest open questions in all of science. Somewhere in our galaxy, there may be tens of billions of worlds resting in that narrow, temperate band where liquid water can exist. Stretch that estimate across the observable universe, and the number swells past billions into the quintillions. At first, the question sounds simple. How many habitable planets are out there? But buried inside it is a problem astronomers still can't solve. We've found thousands of planets beyond our solar system. We've measured their sizes, traced their orbits, and in some cases even read the chemistry of their atmospheres. And still, the true number of potentially habitable worlds remains one of the most uncertain figures in all of astronomy. Astronomers have confirmed nearly 6,000 exoplanets so far, and the data hints that somewhere between 30 and 80% of Sun-like stars may carry an Earth-sized planet in their habitable zone. The numbers are staggering. The math is generous. The right conditions in principle seem to be everywhere, and yet scientists still can't agree on the answer. Because against tens of billions of plausible homes in our galaxy, against quintillions scattered across the cosmos, the number of worlds we know to be inhabited is exactly one. By the end of tonight, you're going to understand how astronomers define a habitable zone, why some of the most promising candidates orbit quiet stars like Ross 128, TRAPPIST-1, and Teegarden's star, and what it means that the gap between tens of billions of possible homes and a single confirmed one remains the most patient silence in science. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. That silence has a shape. It is not the silence of emptiness. It is the silence of a question that has been asked billions of times over and answered so far, exactly once. Think about what that means. Tens of billions of worlds in the Milky Way alone sit at the right distance from their stars for liquid water to exist on their surfaces. Across the observable universe, that number climbs until the word billion becomes useless, and we reach for quintillions instead. A quintillion is a billion billions, and even that number, staggering as it is, represents only the worlds we estimate could be habitable, not the worlds we know are habitable, could be. Here is where the question splits in two, and keeping those two halves separate matters more than almost anything else we will discuss tonight. A world that is habitable could support life, given the right conditions. A world that is inhabited actually does support life. Those two words are often treated as interchangeable in popular coverage of this subject. They are not. They are not even close. The gap between them is the gap between a house with running water and a house where someone lives. One describes infrastructure, the other describes a resident. The entire question of life beyond Earth lives in that gap. We have now confirmed roughly 6,000 exoplanets, worlds orbiting other stars. The candidate count, planets that have shown the right signals but not yet been fully verified, is several times higher. Before the year 2000, we had confirmed almost none. The discovery rate accelerated so quickly that astronomers had to build new statistical machinery just to process what was coming in. Early models suggested that Earth-sized planets in habitable zones would be rare. The data said otherwise. Not rare, common. That was the first surprise. Current best estimates suggest that somewhere between 30 and 80% of Sun-like stars host an Earth-sized planet in their habitable zone. The Milky Way contains roughly 400 billion stars. Even the conservative end of that range applied to a fraction of those stars produces a number measured in the tens of billions. Tens of billions of worlds, where, in principle, the conditions for liquid water on the surface could exist. And yet, the count of worlds we know to be inhabited remains exactly one. That asymmetry is the engine of this entire conversation. Now, those 6,000 confirmed worlds are not a random sample. This is critical. The catalogue is biased, heavily biased, in one particular direction. To understand why, you need to understand how we find these planets in the first place. There are 4 primary methods, and each one sees a different slice of the sky. The first is the transit method. When a planet passes between its star and our line of sight, it blocks a small fraction of the star's light. A telescope watching that star will record a tiny periodic dip in brightness. A Jupiter-sized world crossing a Sun-like star blocks about 1% of the star's light. 1% is detectable. An Earth-sized world blocks about 0.01%. That is the difference between noticing a moth cross a floodlight and noticing a gnat cross it from a mile away. The Kepler Space Telescope and, more recently, TESS, the Transiting Exoplanet Survey satellite, have found thousands of planets this way. But transit detections require edge-on geometry. The planet's orbit has to be aligned almost perfectly with our line of sight. Most orbits are not. So transit surveys see only a fraction of what is out there, and they preferentially see large planets on close, fast orbits, because those transit more often and block more light. The second method is called radial velocity, or the wobble method. A planet does not simply orbit its star. The two objects orbit their shared center of mass. When a planet pulls its star toward us, the star's light shifts slightly toward the blue end of the spectrum. When the planet pulls the star away, the light shifts toward the red. Jupiter, the largest planet in our solar system, pulls the Sun at roughly 13 meters per second. That is a brisk walking pace. Detectable. Earth pulls the Sun at about 9 centimeters per second. That is slower than a snail. We can measure the pull of a Jupiter. Measuring the pull of an Earth, precisely enough to be useful, remains one of the hardest technical challenges in observational astronomy. The third method is direct imaging, physically separating the light of a planet from the overwhelming glare of its star. Think of trying to photograph a firefly hovering 1 inch from a searchlight from across a city. Currently, this works only for young, hot planets on wide orbits. Worlds that glow brightly on their own and sit far enough from their star that the contrast becomes manageable. Next-generation space telescopes will push this boundary considerably, but today, direct imaging has contributed only a small fraction of the catalogue, and mostly at the extreme end of planetary size and orbital distance. The fourth method is gravitational microlensing. When a foreground star passes precisely in front of a more distant background star, the foreground star's gravity acts as a lens and amplifies the background star's light. If the foreground star has a planet, that planet leaves its own signature in the amplification curve. This method detects planets that the other methods miss entirely, cold worlds on wide orbits, and even rogue planets drifting through the galaxy without any star at all. But microlensing is a one-time event. The alignment passes, the opportunity is gone. There is no follow-up observation, no second look, no chance to characterize the atmosphere or measure the mass precisely. Each method, then, sees a different population of planets. Each has blind spots. And when you combine the four catalogues, the composite picture skews heavily toward the transit detections, which means it skews toward close-in, large, fast-orbiting worlds. Correcting for that bias is not a simple calculation. Astronomers have spent years building statistical models to ask, given what we can detect, what does the true underlying population probably look like? The range of 30 to 80% for Earth-sized habitable zone planets around Sun-like stars reflects the honest width of that uncertainty. So what does habitable mean precisely? For the purposes of this video, we will use the conservative definition. A world is habitable if, given an Earth-like atmosphere and reasonable surface pressure, liquid water could persist on its surface for geologically long timescales, not for a season, not for 1,000 years, for hundreds of millions of years or more. Long enough for chemistry to have a chance at becoming biology. This is a deliberate choice. There are broader definitions. Subsurface oceans, exotic solvents, pressure extremes that some microorganisms on Earth can survive. Those are real possibilities and worth discussing. But the conservative definition is the one the catalogue uses, and it is the one we will hold to throughout tonight, because it is the definition that allows the most direct comparison between candidates. Here's what makes this so strange. The conservative definition is the hardest standard to meet, and even by that hard standard, the galaxy appears to be full of candidates. But candidates are not answers. And so far, only one world has crossed from candidate to certainty. The methods that filled the catalogue with thousands of worlds each carry their own limits, their own blind spots, their own populations they cannot see. And as we move from the tools that built the catalogue to the individual worlds the catalogue contains, those limits are going to matter enormously. So let's stay a moment with the definition itself because what seems like a clean concept turns out to carry a great deal of weight inside it. The phrase habitable zone has been in use since the middle of the 20th century, long before the first confirmed exoplanet. It describes an orbital range around a star where a rocky planet with an Earth-like atmosphere could maintain liquid water on its surface. Not underground, not in a pressurized chamber. On the surface, where temperatures stay between 0 and 100 degrees Celsius, where water neither freezes permanently nor boils away. That boundary has two edges, and each one is defined by a specific kind of failure. The inner edge is set by the runaway greenhouse limit. As a planet absorbs more energy from its star, surface water begins to evaporate. Water vapor is itself a greenhouse gas, meaning it traps more heat, which causes more evaporation, which traps more heat. The feedback accelerates. Eventually the oceans boil completely. The water vapor rises high enough to be broken apart by ultraviolet radiation and lost to space. The planet does not merely get warm, it crosses a threshold from which there is no return. The outer edge is set by what is called the maximum greenhouse limit. As a planet drifts farther from its star, the surface cools. To stay warm, the atmosphere would need more and more carbon dioxide. But carbon dioxide has a limit of its own. At high enough concentrations and low enough temperatures, it begins to condense out as ice. The greenhouse effect collapses. The planet freezes. For our Sun, the conservative habitable zone runs from roughly 0.95 to 1.37 astronomical units. 1 astronomical unit is the Earth-Sun distance, about 93 million miles. Earth at 1 AU sits comfortably inside that window, close to the middle. But here's where it gets strange. The solar system did not give us just one data point. It gave us 3. Venus sits at 0.72 AU, just inside the inner edge. Its surface is hot enough to melt lead. Its atmosphere is 90 times denser than Earth's. Its water inventory is gone, lost to exactly the runaway feedback the models predict. Mars sits at 1.52 AU, just outside the outer edge. Its surface is dry and frozen now, but the geology tells a different story. Ancient river channels, lake beds, mineral deposits that only form in the presence of liquid water. Mars had surface water once. Then its atmosphere thinned and the water disappeared. 3 rocky planets in the temperate ring of the same solar system. 1 worked, 2 did not. The solar system has run the experiment 3 times, and the margin between success and failure is narrower than it looks on a diagram. Now, there is a second version of the habitable zone, and it matters because it changes the numbers substantially. The optimistic habitable zone uses the empirical evidence from Venus and Mars themselves. Since Venus shows signs that it may once have hosted liquid water before it crossed the inner threshold, and Mars clearly did host it before crossing the outer one, some researchers draw the boundaries at those points rather than at the theoretical limits. For our Sun, the optimistic zone runs from roughly 0.75 to 1.77 AU. That is approximately twice as wide as the conservative zone. This distinction is not academic. Most headlines about newly discovered habitable worlds use the optimistic definition. Most peer-reviewed statistical studies use the conservative one. Depending on which version you apply, your count of habitable zone planets in the galaxy changes by a factor of roughly 2. The same catalogue of confirmed worlds produces 2 very different answers depending on where you draw the line. The habitable zone also shifts depending on the star. M-dwarf stars, the most common type in the galaxy, are small and dim. Their habitable zones sit very close in, at orbital distances where planets complete a full orbit in a matter of days. F-type and A-type stars, hotter and brighter than our Sun, have habitable zones much farther out, where orbital periods stretch to years. The zone scales with the star's luminosity, and this scaling changes almost everything about what life on those worlds might experience. But none of that changes what the habitable zone fundamentally is. And here is the conceptual pivot everything else depends on. The habitable zone is a temperature window. Only that. It tells you that a planet, given an Earth-like atmosphere, would sit at the right distance to keep water liquid. It says nothing about whether the atmosphere exists at all. It says nothing about whether that atmosphere can survive. It says nothing about the star, the planet's interior, the planet's neighbors, or the planet's history. It is necessary. It is very far from sufficient. Think about how many independent ways a habitable zone planet can still be completely uninhabitable. The atmosphere might be absent entirely, stripped away by stellar radiation before the planet could hold it. It might be too thin to maintain surface pressure. It might be so thick that it triggers the runaway greenhouse the zone was designed to avoid. The planet might be tidally locked, with one hemisphere baked in permanent day and the other frozen in permanent night, a condition common among worlds orbiting close-in M dwarfs. The star itself might be violent, erupting in superflares hundreds to thousands of times more energetic than anything our sun produces, stripping gas from the planetary surface faster than it can be replenished. Even a planet that escapes all of that still needs more. Magnetic fields matter enormously. Earth's magnetic field is generated by liquid iron circulating in the outer core, an active dynamo that deflects the solar wind, the stream of charged particles flowing outward from the sun. Without it, the solar wind gradually erodes the atmosphere from the top down. Mars had a magnetic dynamo once. It shut down roughly 4 billion years ago. Over the next billion years, the Martian atmosphere thinned. The surface dried. Among the rocky worlds in the habitable zone of our own solar system, only Earth still has an active field. Plate tectonics matter just as much. Earth's plates are not just geological features. They are a planetary thermostat. When rocks are exposed to air and water at the surface, they absorb carbon dioxide through a process called chemical weathering. When plates subduct, pulling that rock back into the mantle, volcanism releases the carbon dioxide back into the atmosphere. This cycle has kept Earth's climate roughly stable over billions of years, correcting for increases and decreases in solar output. Venus probably lacks active plate tectonics. Mars almost certainly does. Without that regulation, small perturbations in a planet's energy budget can compound into runaway conditions on timescales of millions of years. The moon matters too, and this is the part most people don't expect. Earth's moon is unusually large relative to its planet. It keeps Earth's axial tilt stable at roughly 23.5 degrees over billions of years. That stability matters for climate. A planet whose axial tilt wanders dramatically can swing from temperate to extreme and back again on geological timescales. Earth's moon formed from a collision with a Mars-sized body early in the solar system's history. That kind of collision is probably rare. Most rocky planets probably don't have large stabilizing moons. And then there is the question of where in the galaxy a system forms at all. The Milky Way is not uniformly hospitable. Near the galactic center, stellar density is high and supernova rates are high. Radiation environments there can sterilize planetary surfaces and strip atmospheres over time. Far from the center, the concentration of heavy elements drops below the level needed to form rocky planets in the first place. Rocky planets require iron, silicon, magnesium, oxygen, elements forged in earlier generations of stars. In the outer galaxy, those elements are too scarce. What remains is a thin ring, sometimes called the galactic habitable zone, running roughly from 7 to 9 kiloparsecs from the galactic center, where kiloparsecs are units of distance astronomers use for galactic scales. Our sun sits at about 8 kiloparsecs, squarely in the middle of that ring. Estimates suggest that somewhere between 20 and 30% of all stars in the Milky Way fall within that annular region. The habitable zone is the address on the envelope. Whether life is inside depends on what is in the letter. Two planets can share the same address and contain completely different contents. The address tells you where to look. It does not tell you what you will find. A confirmed habitable zone planet is the first step. It is not the answer. Determining what is actually in that letter, reading the atmosphere for chemical signatures, looking for gases that only biology produces, watching long enough to know whether those signals persist, requires instruments that do not fully exist yet, and characterization programs that will take another 2 decades to complete. And the worlds already in the catalogue, waiting to be read, are stranger than most of the headlines suggest. And those worlds, the ones already waiting in the catalogue, are stranger than even that picture suggests. Both the conservative and the optimistic habitable zones share an assumption so obvious it is almost invisible. They assume life lives under a sky. They assume a sunlit ocean, a thin atmosphere above it, a surface you could stand on and look up from. That assumption is built entirely on Earth. It may not describe the most common form of habitable place in the galaxy. Over the past 2 decades, researchers have gradually loosened that definition. Not all at once, and not without argument, but 6 broader categories have emerged, each one stretching the count of plausible homes further out. And what they reveal, taken together, is that we have been looking at the wrong kind of place. The first stretch starts in our own solar system, and it is the most unsettling. The largest reservoirs of liquid water in our solar system are not on Earth's surface. They are beneath ice, far from any temperature-defined habitable zone, hidden under crusts tens of kilometers thick, kept liquid not by sunlight, but by something else entirely. Europa, a moon of Jupiter, has a global ocean beneath an ice shell somewhere between 10 and 30 kilometers thick. That ocean is in contact with a rocky seafloor, and where ocean meets rock under pressure, the chemistry can drive the same kind of reactions that power life at Earth's mid-ocean ridges, places where hydrothermal vents push mineral-rich water up through the seafloor and sustain entire ecosystems with no sunlight at all. Europa's ocean may be doing the same thing. Enceladus, a moon of Saturn, goes further. It does not just have a subsurface ocean, it is leaking it into space. Cryovolcanic plumes erupt from its south pole, spraying water, salts, simple organic compounds, and molecular hydrogen into Saturn's ring system. We have flown a spacecraft through those plumes. We have tasted that ocean from the outside. The hydrogen alone is a signal. On Earth, the reaction between hydrogen and carbon dioxide is one of the oldest energy sources life uses. Ganymede and Callisto, 2 more of Jupiter's moons, likely have subsurface oceans of their own. Titan, Saturn's largest moon, has surface lakes of liquid hydrocarbons and a deep water ocean buried beneath. Triton, Pluto, several Kuiper Belt objects. The list keeps extending. Add the total estimated liquid water beyond the solar system's snowline, out past the frost boundary where ice persists, and it exceeds Earth's total surface water by a factor of more than 30, not slightly more than 30 times over. The implication is significant. A small rocky moon, tidally flexed by the gravity of a giant planet at almost any orbital distance, can sustain a long-lived liquid ocean. No star required, no temperature window required, no sky required. And some calculations suggest the total habitable volume in the galaxy, measured by subsurface liquid water rather than surface conditions, exceeds the habitable volume measured by Earth-like surface planets by many orders of magnitude. That was the first category. The picture gets stranger. Researchers have hypothesized a class of world they call Hycean worlds, the name built from hydrogen and ocean. The idea is a sub-Neptune-sized planet, somewhere between 1 and 3 times Earth's radius, with a thick hydrogen atmosphere wrapped around a global liquid water ocean beneath. The hydrogen envelope acts as insulation. It traps heat. The ocean beneath can remain liquid even at equilibrium temperatures far below what would freeze an open surface. If this class of world actually exists as a stable configuration, it could roughly double the count of potentially habitable worlds in the galaxy. It has not been confirmed yet. The category is hypothesized, not observed. But the physics does not rule it out, and the implications of ruling it in are significant. Then there are the tidally locked worlds. Most planets in the habitable zones of red dwarf stars, the most common type of star in the galaxy, are probably tidally locked. One face permanently toward the star, one face permanently away, the day side scorched, the night side frozen. For decades this seemed to settle the matter. Tidally locked meant uninhabitable, but modern climate modelling has softened that conclusion considerably. Even a modest atmosphere can transport heat. Wind moves from the hot side to the cold side. The distribution is not uniform. Around the boundary between day and night, the terminator, a ring of permanent twilight can persist where temperatures are moderate. Not warm, not cold enough to collapse. Life could in principle exist in that ring, beneath a sky in which the sun never sets, dim and red, hanging fixed on the horizon for billions of years. This has not been observationally confirmed, but it is the major reason researchers do not entirely rule out habitability for the galaxy's most numerous class of star. Beneath ice, deeper still, is a fourth possibility. A planet entirely outside any temperature-defined zone, its surface locked under a global sheet of ice, could still be habitable at the boundary between rock and ice below. Geothermal heat from radioactive decay in the planet's interior, hydrothermal vents, chemical disequilibrium at the rock-ice interface. We have a terrestrial example. Lake Vostok, buried under nearly 4 kilometers of Antarctic ice, hosts a microbial community that has been sealed from the surface for millions of years. It lives on chemical energy. No sunlight, no open water. Just rock and chemistry and patience. If that works on Earth, there is no reason it requires Earth's address. But something else was happening. The fifth category removes the star entirely. The Milky Way contains an estimated several 100 billion rogue planets, worlds that either formed without host stars or were ejected from their original systems by gravitational encounters. Recent microlensing surveys, which detect mass by its gravitational distortion of background starlight, suggest rogue planets may actually outnumber stars in the galaxy by a factor of several. They drift through the dark between star systems. They have no light, no orbital seasons, no parent, and yet, a large rogue world, a super-Earth or Neptune-mass planet, generates its own heat from the slow decay of radioactive elements in its interior. That heat can keep a subsurface ocean liquid for billions of years. A rogue planet with a thick hydrogen atmosphere can insulate that heat even further. It becomes, essentially, a closed system, warm inside, cold and dark outside. The galaxy may contain more potentially habitable rogue worlds than habitable worlds orbiting stars. The sixth category is the one we have yet to find beyond our own system. Exomoons. Large moons orbiting giant planets. Our solar system is instructive here. Count the potentially habitable worlds in it by the standards of subsurface oceans alone, and you reach Europa, Enceladus, Titan, Ganymede, Callisto, 5 moons before a single planet. The planets, by those broader standards, produce only Earth on the surface and Mars as a historical possibility. The moons outnumber them. If that ratio holds across the galaxy, and there is no particular reason it should not, then there is a vast population of potentially habitable exomoons orbiting giant planets. Some of them inside their host star's habitable zone. Some of them tidally heated regardless of orbital distance. We have not confirmed a single exomoon yet. Detection is at the edge of what current instruments can do. But the first confirmed habitable exomoon would shift the count substantially. It would shift the way we think about where to look. Taken together, these 6 categories point towards something that does not quite look like the picture most people carry. The galaxy is not divided into a narrow inhabited ring and a vast sterile wasteland. It is more like a slow scattering of pockets, most dark, most hidden, most sealed beneath ice or wrapped in hydrogen or drifting without any star to warm them at all. Small, isolated, quiet. The conservative count, the one this survey will mostly use going forward, is the floor, not the ceiling. The surface water under a sky definition is the place to start because it is the only kind of habitability we can observe from a distance, the only one our telescopes can currently reach for. But the softer definitions remain, as a quiet reminder underneath everything that follows. Every time the count appears too small, remember that it does not include the hidden oceans, the rogue worlds drifting alone in the dark, or the Terminator rings where dim red light has hung at the horizon for 1 billion years. The conservative count is where we begin. What that count actually looks like is the next question. That count starts here. The first named world in this catalogue sits in the constellation Cygnus, about 620 light-years away. Its name is Kepler 22b, and in late 2011, it became the first planet confirmed to orbit inside the habitable zone of a star that closely resembles our own Sun. Before Kepler 22b, the question of whether any other star hosted a planet at the right temperature had been purely statistical. Scientists could estimate the probability. They could argue about the frequency, but they had no example. Kepler 22b made it an example. That is what the confirmation meant. Not a model, not a prediction. A planet in the right place around the right kind of star. The star it orbits, designated Kepler-22, is a G-type star, the same broad category as our Sun. Its surface is roughly 300 degrees cooler. Its radius is about 97% of the Sun's. Its luminosity is about 79% of the Sun's. A slightly smaller star, slightly cooler, slightly dimmer. Not a different kind of star. A quieter version of our own. The planet takes 290 Earth days to complete one orbit. Its semi-major axis, the average distance between planet and star, sits at about 0.85 AU. That places it comfortably within the habitable zone. Its equilibrium temperature without any atmosphere would be roughly 260 Kelvin, which is about minus 12 degrees Celsius. Cold. But if the planet carries an Earth-like atmosphere, the surface would warm to roughly 15 degrees Celsius. That is almost identical to Earth's average surface temperature. When scientists calculated its Earth Similarity Index, a scoring system for how closely a planet's conditions resemble Earth's, Kepler-22b scored 0.84 out of a possible 1.0. On paper, this is as close as anything had come. But something was wrong. The planet's radius is approximately 2.4 times Earth's. That single measurement, the radius, is almost the only solid thing we know about the planet's physical body, and it sits in a deeply ambiguous place on the spectrum of planetary types. Above roughly 2 Earth radii, planets may be rocky worlds with thick atmospheres, or they may be mini-Neptunes, gas-rich and without a solid surface, or they may be something in between, volatile-rich, wrapped in deep water, ocean stretching from pole to pole with no land anywhere. Without a mass measurement, there is no way to distinguish between these possibilities. 3 options: rocky and heavy, with surface gravity much stronger than Earth's, and a thick, crushing atmosphere above. Volatile rich and wet, an ocean world with no continent and no shore. Or gaseous, with no rocky surface at all. Researchers leaning toward the ocean world interpretation have pointed out that for the planet to be purely rocky at its size, its density would need to be unusually high. The more plausible fit, they argue, is a global ocean, tens or hundreds of kilometers deep, with a thick atmosphere above and water stretching to every horizon. Not a metaphor, a literal possibility. Water stretching from horizon to horizon, indifferent to whether anything has ever swum through it. Around the time of the announcement, informal interviews with researchers produced some striking figures. Individual scientists suggested there was a 95 to 99% probability of life on Kepler-22b. Those numbers spread widely. They captured something real about the excitement in the field. Habitable zone planets around sun-like stars had been expected to be rare. The data was beginning to suggest they were not. That discovery was genuinely astonishing, and the enthusiasm was genuine. But those figures were enthusiasm, not formal probability assessments, not consensus, enthusiasm. More than a decade later, the honest position is this: Kepler-22b is in the habitable zone. That is confirmed. Almost everything else is open. We do not know whether the planet has a surface. We do not know whether it has an atmosphere. We do not know whether it rotates freely like Earth, or is tidally locked with one face permanently toward its star. We do not know whether its host star has been quiet enough across billions of years to allow an atmosphere to survive. A not-quite Earth orbit around a not-quite Sun, and beyond that, almost nothing is settled. That uncertainty does not diminish what the discovery was. Kepler-22b opened a door. Every candidate that came after it, including all the ones that follow here, followed through that door. But the door and the room behind it are different things. In 2015, scientists announced the next milestone: a planet called Kepler-452b. The press gave it a name almost immediately: Earth's older cousin. The host star, Kepler-452, is a G-type star with a surface temperature within 20 degrees of the Sun's. Slightly larger, slightly brighter, and older. Significantly older. Kepler-452 is approximately 6 billion years old, making it roughly 1.5 billion years older than the Sun. The planet orbits at about 1.05 AU, just outside Earth's orbital distance. Its year is 385 Earth days, within 5% of an Earth year. Its radius is about 1.6 times Earth's. Its estimated mass is roughly 5 times Earth's, giving it a surface gravity approximately twice what we experience here. The most striking thing about Kepler 452b was not its size or its orbital distance. It was its age. Think about what a billion years means in biological terms. By the only example we know, a billion years is the difference between a planet of single-celled microbes and a planet of conscious organisms looking back at the sky. Earth took roughly 4 billion years from its formation to produce complex multicellular life. Kepler 452b, if it has been habitable across its history, has had longer than that. If the same biological trajectory that played out on Earth had begun there, it began with more time to run. But here is the problem. Stars do not stay constant. Main sequence stars brighten by roughly 10% per billion years. As a star brightens, the inner edge of its habitable zone moves outward. Kepler 452b sits near the inner edge of its star's conservative habitable zone, which means that as Kepler 452 has aged and brightened, the planet has been absorbing more energy each billion years. It may now be receiving enough stellar flux to push it into the early stages of a runaway greenhouse, not abruptly, too slowly to observe directly. But the transition that turned Venus from a potentially temperate world into a furnace may be happening, or may have already happened, at Kepler 452b. 1.5 billion additional years of sunlight does not only mean more time for life, it also means more time for the star to inch its inner habitable zone outward past the planet it once comfortably held. Wait, there is something else. In 2018, a follow-up statistical analysis raised the possibility that the original detection of Kepler 452b may have been a false positive, a pattern in the data produced by noise in the host star rather than a transiting planet. The detection has not been formally retracted. Mainstream catalogs still list the planet as confirmed, but the confidence is weaker than it was at announcement. The older cousin may not be real. 2 other members of the Kepler catalog deserve their place here. Kepler 186f was announced in 2014. It was the first Earth-sized planet confirmed in the habitable zone of any star. Its radius is about 1.11 times Earth's. It orbits an M-dwarf star about 580 light-years away, with a period of 129 Earth days. Its equilibrium temperature without an atmosphere would be roughly 180 Kelvin, around minus 93 degrees Celsius. It would need a thick atmosphere to hold liquid water at its surface. The standard caveats for M-dwarf worlds apply. Possible tidal locking, possible flare activity, but it earned its place in the catalogue as the first Earth-sized world in any star's habitable zone. Kepler 1649c was confirmed in 2020, not from new observations, but from a reanalysis of older Kepler data that had initially been misclassified. The planet is approximately 1.06 times Earth's radius, which places it among the most Earth-sized candidates in the catalogue. It orbits an M-dwarf about 300 light-years away, with a period of just 19.5 days. It receives about 75% of the stellar flux Earth receives from the Sun, placing it in a temperature range that could support liquid water with the right atmosphere. Its Earth similarity index is among the highest of any confirmed exoplanet. And then there is a stranger question underneath all of these. A small but growing body of scientific work asks whether Earth itself is the optimum, whether the planet we live on is the best possible template for life, or merely one configuration among several that could do as well or better. The superhabitable hypothesis proposes a set of criteria for worlds that might be more hospitable to life than Earth. The criteria include a mass between 1 and 3 times Earth's, giving the planet stronger gravity to hold a thicker atmosphere and more geological activity to recycle nutrients, a radius between 1.1 and 1.3 times Earth's, a surface temperature roughly 5 degrees Celsius warmer than Earth's average, encouraging greater biological diversity, and a K-type host star, slightly cooler and smaller than the Sun, with a main sequence lifetime ranging from 20 to 70 billion years, more than twice the Sun's expected 10 billion. A planet around a K-type star in the right zone would have more time to develop complexity before its star faded. Some proposals also include a moon larger than Earth's, for stronger tidal mixing and more stable axial tilt. Candidates in the literature that score well against these criteria include KOI 5750.01, KOI 5541, Kepler 1126b, Kepler 69c, and Kepler 1638b. None of them are confirmed super habitable. They simply meet enough of the proposed criteria to be worth noting. The hypothesis flips the standard question. We tend to ask whether a world is as Earth-like as possible, as if Earth is the measurement and deviation is a penalty. But we have one example of a world that produced life. That is not enough to know whether Earth represents the optimum or simply one configuration that worked. Maybe a slightly warmer, slightly larger, slightly older world around a slightly smaller and longer-lived star would produce more life, more quickly, across more time than Earth has managed. We do not know. We have one example, and the one example is us. The catalogue does not end with Kepler. The next candidates came from a different kind of star, and they brought a different set of surprises. That catalogue does not end with Kepler, and the next candidates came from a completely different direction. Not hundreds of light years away, not thousands, 4.24 light years. The nearest star to our Sun has a planet, and that planet sits inside its habitable zone. The star is Proxima Centauri. It is the smallest and dimmest of the three stars in the Alpha Centauri system, bound gravitationally to the better-known pair, Alpha Centauri A and B, at a distance of roughly 12,000 astronomical units, tracing a slow orbit around them that takes about 550,000 years to complete. Proxima is an M-type red dwarf. Its mass is about 1/8 of the Sun's. Its luminosity is roughly 1/17,000th of the Sun's. Despite being the closest star to Earth, it is completely invisible to the unaided eye. It shines too faintly, and the sky swallows it entirely. For most of human history, we did not even know it was there. In late 2016, astronomers announced that a planet had been detected orbiting Proxima Centauri. They found it through the radial velocity method, detecting the faint gravitational wobble it produced in the star. That wobble repeated every 11.2 Earth days. The planet's minimum mass came out to 1.07 times Earth's mass. Its orbital distance was 0.049 astronomical units. To put that in context, Mercury sits 8 times farther from the Sun than Proxima b sits from its star. The planet is almost impossibly close to its host, and yet it sits in the habitable zone. That is the first surprise. Proxima is so dim that even at 0.049 AU, the planet receives roughly the same amount of stellar energy that Earth receives from the Sun. The equilibrium temperature, meaning the surface temperature with no atmosphere at all, works out to about 234 Kelvin, or roughly minus 40 degrees Celsius. That is cold, but cold is not the same as uninhabitable. With a thick enough atmosphere, the surface could warm into the range where liquid water is stable. By the simplest possible reading, Proxima b is a rocky planet of roughly Earth mass, sitting in the habitable zone of the nearest star. Statistical corrections for orbital inclination push the expected true mass to somewhere between 1.3 and 1.4 Earth masses. The numbers looked extraordinary, but here's where it gets strange. At 0.049 AU, Proxima b is almost certainly tidally locked. Tidal locking happens when a planet orbits so close to its star that gravitational forces slow its rotation until one face permanently points toward the star and the other permanently faces away. The day side bakes. The night side freezes. Without an atmosphere capable of transporting heat from the warm hemisphere to the cold one, the difference between those two faces would be lethal. Winds would circulate, carrying some warmth toward the dark side, but how much depends entirely on how thick the atmosphere is. One possible outcome, if the atmosphere survives, is a narrow terminator ring, the line between permanent day and permanent night, where temperatures might stay moderate for billions of years. A dim red star hanging perpetually on the horizon, the sky always at twilight, neither fully lit nor fully dark. That is the optimistic version. The second complication is the star itself. Proxima Centauri is a flare star. During strong flare events, the flux reaching the planet's surface can spike to somewhere between 100 and 1,000 times the equivalent flux Earth receives during a powerful solar event. Not a small difference. Not a manageable difference. Over 4 billion years of repeated bombardment, that kind of activity can strip an unprotected atmosphere entirely. If Proxima b lacks a strong magnetic field, and we do not know whether it does, the stellar wind and radiation would erode whatever atmosphere formed. The very conditions that make the planet's temperature placement look so promising may have been undone by the star it orbits. The honest reading is this: Proxima b is the floor of the optimism spectrum. It may be the nearest habitable world. It may equally be an airless rock, sitting in the right orbital range with nothing left to show for it. What we have is a mass and an orbital period. What we do not yet have is an atmosphere. Next-generation ground-based telescopes, currently under construction, should be capable of directly imaging Proxima b and capturing atmospheric spectra. Within 10 to 15 years, the question of whether the planet holds any atmosphere at all should have an answer. Not a guess, an answer. The instruments are being built. Proxima b is not the only world in the system. In 2020, astronomers reported a second candidate, Proxima c, a super-Earth of roughly 7 Earth masses orbiting at about 1.5 astronomical units, well outside the habitable zone and not a habitability target. In 2022, a third candidate appeared in the data, Proxima d, a small inner world with a mass of only about 1/4 of Earth's and an orbital period of roughly 5 days. Proxima d is not habitable, but it tells us something important. The Proxima system is packed. M-dwarf systems frequently host multiple planets in tight orbital configurations. The system is more complex than a single interesting candidate. The two larger stars in the Alpha Centauri system are a different matter. Alpha Centauri A is a G2V star, essentially identical to the Sun in surface temperature and only marginally larger. Alpha Centauri B is a K1V star, slightly smaller and cooler. The two orbit each other over a period of roughly 80 years, swinging between a closest approach of about 11 astronomical units, roughly the distance of Saturn from our Sun, and a farthest separation of about 36 astronomical units, near Neptune's distance. At those separations, stable planetary orbits within the habitable zones of both stars are gravitationally possible. Neither star is known to be pulling its companions' planets apart. In 2024, a direct imaging program using the James Webb Space Telescope reported a candidate around Alpha Centauri A. The result is preliminary. It is not confirmed, but the inferred orbital distance places the candidate roughly within the star's habitable zone. That is worth holding carefully, not as a discovery, as a lead. The Habitable Worlds Observatory, a telescope concept currently in development for the 2040s, is specifically designed to image Earth analog planets around stars like Alpha Centauri A. The nearest Sun-like star may already be showing us something. We do not yet know what it is. Beyond the Alpha Centauri system, the nearby stellar neighborhood contains several more candidates that have accumulated in the catalogs over the last decade. Ross 128b, 11 light-years away, is a rocky planet of about 1.35 Earth masses, orbiting an M-dwarf that is unusually quiet by the standards of its class. Low flare activity is meaningful for habitability prospects. A calm star gives an atmosphere a better chance of surviving. Teegarden star B and C, at 12.5 light-years, are two Earth mass candidates in the habitable zone of an old, quiet M-dwarf, and their Earth Similarity Index scores rank among the highest in the confirmed catalogue. Tau Ceti, a G8V star about 12 light-years away, hosts two candidate super-Earths, designated E and F, that may sit in or near its habitable zone. The detections remain debated. Wolf 1061c at 14 light-years is a super-Earth of roughly 4 Earth masses, sitting near the inner edge of its M-dwarf host's habitable zone. Gliese 666ce at 23 light-years is a super-Earth of about 3.8 Earth masses, firmly inside the habitable zone of an M-dwarf that is itself part of a triple-star system. None of these are confirmed inhabited. None of them are confirmed to hold atmospheres capable of sustaining surface liquid water. They are candidates. What they tell us, taken together, is that within a few dozen light-years of the Sun, there are already multiple plausible targets for surface or near-surface habitability. The nearest fully confirmed Earth analog around a Sun-like star may still be waiting to be detected, But the neighborhood is not empty of possibilities, and the instruments being built right now may be capable of answering the atmosphere question for the closest of them within a single human generation. The most interesting results from that neighborhood may still be ahead. A little further out, past Teegarden's star, the catalogue walk reaches something different in kind. Not just another candidate, not another single world tagged with a probability and a question mark. An entire system, 7 planets, 1 star, one of the most studied collections of worlds beyond our own. TRAPPIST-1 sits 39.6 light-years from Earth. In this catalogue, that is not far, and what sits there has reshaped how seriously astronomers think about M-dwarf habitability as a class. The name comes from a small telescope in Chile. TRAPPIST, the transiting planets and planetesimals. Small telescope detected the first signs of planetary transits around this star in 2015. What it found, and what follow-up observations confirmed, was a system that barely seemed real. 7 rocky planets, all of them roughly Earth-sized, 3 of them sitting inside the habitable zone of their host star. But before we look at the planets, we have to look at the star, because the star is where this system gets strange. TRAPPIST-1 is classified as an M8V ultra-cool dwarf. Its mass is about 0.089 times the mass of our Sun. That number sits almost exactly at the lower boundary for hydrogen fusion. Below that threshold, a body cannot sustain the nuclear reactions that define a true star. TRAPPIST-1 clears it. Barely. It is barely a star at all. Its radius is about 0.121 solar radii, only slightly larger than Jupiter. Its surface temperature is roughly 2,500 Kelvin, a dim red ember compared to the Sun's bright yellow-white 5,800 Kelvin. Its luminosity is about 0.05% of the Sun's. It produces almost no light by stellar standards. It is quiet and small and ancient. Its age is approximately 7.6 billion years, more than 3 billion years older than our own Sun. And here is the part that matters most for what comes next. Stars of this size and mass are expected to remain on the main sequence for hundreds of billions of years. Some models put the upper limit at close to 1 trillion years. The Sun will exhaust its hydrogen in roughly 5 billion more years. TRAPPIST-1 will still be fusing hydrogen long after every Sun-like star in the Milky Way has died. The system will be one of the last lights still burning in the galaxy. That is the time horizon this star offers. And then you look at what orbits it. The 7 planets sit in a tightly packed, resonant chain. Their orbital periods are not random. Planet B completes 1 orbit in 1.5 days. Planet C in 2.4 days. Planet D in 4 days. Planet E in 6.1 days. Planet F in 9.2 days. Planet G in 12.4 days. Planet H in 19 days. The ratios between these periods are mathematically linked. Each planet's orbital period is related to its neighbors in a chain of 3 body resonances, the same kind of gravitational relationship that locks Io, Europa, and Ganymede around Jupiter, but scaled up to planetary distances and extended across 7 worlds. That chain has held the system stable for billions of years. The entire system fits comfortably inside the orbit of Mercury around our Sun. 7 worlds, stacked into an arrangement smaller than the innermost slice of our solar system. From the surface of any one of those worlds, the others would not look like points of light. They would look like disks. At closest approach between TRAPPIST-1e and TRAPPIST-1f, an observer on either world would see the other as a disk roughly twice the apparent size of our moon, large enough to show surface features. 2 ships at anchor in the same harbour, close enough to see each other's details clearly. Planet radii across the system run from about 0.77 to 1.13 Earth radii, none significantly larger or smaller than Earth. Bulk densities are consistent with rocky compositions, possibly with some volatile material in the outer planets. These are not gas giants. They are not ocean worlds by radius alone. They are rocky, compact, and Earth-sized. 3 of them sit in the habitable zone. TRAPPIST-1e is the one that draws the most attention. Its radius is about 0.92 Earth radii. Its mass is roughly 0.69 Earth masses. Its orbital period is 6.1 days. It sits firmly inside the habitable zone of its host star, and its Earth similarity index, a scoring system that combines size, density, temperature, and orbital position into a single comparison against Earth, comes in at approximately 0.95 out of 1.0. That is the highest score of any confirmed exoplanet in the catalogue. Nothing else comes close. TRAPPIST-1F sits at the centre of the habitable zone, radius roughly 1.04 Earth radii, orbital period 9.2 days. TRAPPIST-1G sits near the outer edge, radius roughly 1.13 Earth radii, orbital period 12.4 days. 3 worlds in the right temperature window, around a star that will keep burning for trillions of years. The system became one of the highest priority targets for the James Webb Space Telescope, and JWST delivered its first results on the inner planets, on TRAPPIST-1b and TRAPPIST-1c. The results were not what the field had hoped. Both B and C show no detectable thick atmospheres. Dayside brightness temperatures are consistent with bare rocky surfaces, sitting in direct thermal equilibrium with the star. No evidence of atmospheric heat being transported from the day side to the night side. The innermost planets appear to be naked rock, like Mercury, but smaller and dimmer, orbiting a star far cooler than our Sun. Not slightly discouraging, significantly discouraging. The implication reaches outward. TRAPPIST-1's age is 7.6 billion years. That's a long time for a small, active star to irradiate close-in planets. Stellar wind, ultraviolet radiation, and X-ray flux all work on an atmosphere over geological time. The inner planets have apparently lost that fight. Whether the outer 3, E, F, and G, have also lost it is the question the field is now holding carefully. First, direct atmospheric measurements of those 3 habitable zone planets are being analysed. The results will take time, but the early data from the inner planets has shifted expectations. What was once the field's strongest multi-planet test case for M-dwarf habitability is now also its clearest demonstration of what can go wrong over 7.6 billion years of stellar exposure. And yet, even if all 3 habitable zone planets turn out to be bare rock, the system does not lose its significance. 7 Earth-sized worlds in resonance around a star that will outlast essentially everything else in the galaxy is not nothing. If life exists anywhere in that system, in any subsurface environment, shielded beneath rock from the surface radiation, it has the longest possible time horizon available anywhere we have yet found. Not billions of years of stability, hundreds of billions, possibly a trillion. The JWST results on the inner planets are a reason for caution. They are not a reason to look away. The habitable zone observations are still arriving, and TRAPPIST-1 will still be burning long after we have found out. The catalogue continues past TRAPPIST-1, past the 7-world resonant chain, past the long time horizon of that small red ember. It continues into something larger and stranger, a planet that does not fit the category we have been building toward. We have been talking, through all of this, about rocky worlds, surfaces, the kind of planet where water could pool in basins, where rain could fall, where something walking across the ground might look up at a sky. That is the template. That is the assumption. K2-18b is something else entirely. It sits 124 light-years from Earth, in the constellation Leo. Its host star, K2-18, is a red dwarf, smaller and dimmer than the Sun, slightly more active than the quietest M-dwarfs in the catalogue. K2-18b orbits that star every 33 days, at a distance of 0.143 astronomical units. By the numbers, it sounds close, but its star is cool enough that this orbit falls inside the habitable zone. The equilibrium temperature without any atmosphere is roughly 255 Kelvin, about minus 18 degrees Celsius. But here is what separates K2-18b from every world we have covered so far. Its mass is approximately 8.6 times Earth's. Its radius is about 2.6 times Earth's. Those two numbers together place it in a category astronomers call volatile rich. It is too large and too low density to be a solid rocky world like Earth, but it is too small and too dense to be a true mini Neptune with a thick gaseous envelope stretching thousands of kilometers deep. Something else fits. A thick hydrogen atmosphere sitting above a global liquid water ocean. A world where the sky is made of hydrogen and the surface beneath the clouds is not rock. It is water, stretching from horizon to horizon, with no shore. This is what a Hycean world looks like. The name comes from hydrogen and ocean pressed together. It is a hypothesis about a new class of potentially habitable planet. Not a rocky surface world, not a gas giant. Something in between, with an architecture that might support liquid water at depths no telescope can see directly. K2-18b is the first and best studied candidate for this class. In 2023, astronomers published the results of a JWST atmospheric analysis of K2-18b. What they found was striking. The atmosphere showed clear detections of methane and carbon dioxide. Those molecules were not surprising on their own, but the analysis also found something notable by its absence. There was no ammonia. That absence matters. A pure mini-Neptune with a deep hydrogen envelope and no liquid water beneath it would be expected to show ammonia in significant quantities. The absence of ammonia, combined with the presence of methane and carbon dioxide, is consistent with the Hycean model. Chemical or biological processes on or above a hydrogen ocean world would consume ammonia and produce methane in roughly the proportions JWST detected. A pure gas world would not produce this signature. Not a definitive answer. A strong consistency check. The atmospheric fingerprint matched what a Hycean world would show. And then came something else entirely. The same analysis reported a tentative detection of dimethyl sulfide. Dimethyl sulfide is a small organic molecule. On Earth, it is produced almost exclusively by marine microorganisms. Phytoplankton in the upper layers of the ocean generate it in enormous quantities. It is one of the reasons the ocean smells the way it does. No significant abiotic process on Earth produces it in measurable concentrations. It is, in the language of astrobiology, a biosignature gas, a molecule whose presence points toward life. If the dimethyl sulfide signal in K2-18b's atmosphere is real, it would be the most suggestive biosignature ever detected on any world beyond our own. But the answer was stranger than expected. The signal is faint. The statistical confidence is low. Follow-up observations have produced mixed results. Some teams report strengthened evidence for the detection. Others argue that variations in methane concentration can produce spectral features that mimic the dimethyl sulfide signature. The question is not settled. It may not be settled for several more years. This is where honest framing matters. K2-18b shows the most suggestive biosignature observations we have found on any exoplanet. Its atmospheric chemistry is consistent with the Hycean model. Its chemistry is tentatively consistent with biological activity, but consistent with is not the same as confirmed. The detection is real enough to take seriously. It is not firm enough to announce. The next several years of JWST observations, combined with the extremely large ground-based telescopes now under construction, will refine this substantially. By the late 2020s, the question of whether K2-18b is genuinely a Hycean world, with chemistry driven by living organisms, should be much closer to an answer. K2-18b is not alone in the Hycean candidate list. The catalogue holds others. TOI 1452b sits roughly 100 light-years away, with a radius of about 1.7 times Earth's, orbiting an M-dwarf in the habitable zone. Its bulk density suggests a significant water component. Whether it has a hydrogen atmosphere consistent with the Hycean model is not yet established, but the data does not rule it out. LHS 1140b is closer, at 49 light-years. It is a super-Earth in the habitable zone of its red dwarf host. Recent JWST observations have raised the possibility that it may also carry a hydrogen-rich atmosphere over an ocean world interior. Kepler 138d at 218 light-years is an ocean world candidate based on density measurements alone. It is not firmly inside the habitable zone, but its composition suggests substantial liquid water layers at depth. Perhaps a dozen named candidates now populate the broader Hycean list in the catalogue. None of them are confirmed habitable worlds. Several of them show atmospheric chemistry or bulk densities consistent with the Hycean model. The class itself is unconfirmed, but it is no longer just a theoretical possibility. The implications, if the Hycean class turns out to be real, are significant. The conservative habitable zone applies to rocky surface worlds, where liquid water sits exposed to starlight under a thin atmosphere. Sub-Neptune worlds with thick hydrogen atmospheres extend that range considerably. Hydrogen is an excellent insulator. A Hycean world can maintain liquid water at orbital distances that would be far too cold for an Earth-like rocky planet with a thin atmosphere. The effective habitable zone grows larger. The population of potentially habitable worlds grows larger with it. There is also a detection advantage. Hycean worlds are much easier to study than rocky Earth analogues. A thick hydrogen atmosphere produces strong, clear spectroscopic features that JWST can read with relatively short observation times. Characterizing a rocky planet's thin atmosphere takes far more telescope time and is far harder to accomplish from 100 light-years away. If Hycean worlds are common, and if they carry biosignature gases, the first confirmed detection of biology beyond Earth may not come from a rocky world at all. It may come from a planet like K2-18b. The Hycean candidates are not the only exotic possibilities worth naming. Some models describe worlds called eyeball Earths. These are tidally locked planets where one hemisphere permanently faces the star and the other permanently faces away. The day side can maintain a liquid water ocean inside a permanent region of sunlight. The night side freezes. From any vantage point in space, the planet would show a distinct disk of blue ocean centered on the day side, ringed by a continuous ice cap where the frozen night side begins. The geometry, seen from above, resembles a literal eye, dayside ocean as the iris, encircling ice as the white. Below the surfaces of frozen worlds, where the rogue planets sealed away from any star or worlds, where the surface has long since lost its atmosphere, internal heat from radioactive decay can sustain liquid water at the rock-ice interface. These worlds would carry no light, no sky, no wind, just buried ocean in permanent darkness, heated from below. And then there are exomoons. Giant planets can orbit in habitable zones, and giant planets have moons. A moon large enough around a planet in the right orbital range could maintain liquid water on its surface. No confirmed exomoon exists yet in the catalogue. Detection is at the edge of current instrument capability, but if our solar system's ratio of habitable environments holds at all, there are more habitable moons than habitable planets scattered through the galaxy. The catalogue is not simply growing longer, it is growing wider. The number of distinct architectures in which liquid water could persist, in which chemistry could proceed long enough for something remarkable to happen, is increasing faster than the number of confirmed worlds. We are learning that the question is not only how many planets, it is how many kinds. 124 light-years away in Leo, K2-18b continues its 33-day orbit around a small red star. Above the clouds, if there are clouds, a hydrogen sky. Beneath them, perhaps a global ocean turning slowly in the dark. The chemistry is right. The temperature is right. We don't yet know whether anything is alive in it. But the next few years will be different from the last few. The instruments are pointed. The observations are accumulating. And the answer, when it comes, will reshape everything we have been counting. That answer is still accumulating. But step back from K2-18b for a moment. Step back from the hydrogen sky and the possible ocean and the uncertain signal. Step back from all the headline systems, from TRAPPIST-1 and Proxima b and Kepler-22b, and let the wider catalogue come into view. It is long, much longer than most people realize. Beyond the famous names, beyond the systems that made the press conferences, there is a quieter inventory. Dozens of confirmed and candidate habitable zone worlds, most known only by a transit depth and an orbital period. Most holding no record for anything. Most discussed only in papers that begin with catalogue numbers and end with the phrase, "Further observations are warranted." They are the background of this search, and the background is enormous. Take Gliese 500 In 2010, it was announced as one of the first planets detected that might sit squarely in a habitable zone. It orbited an M-dwarf 20 light-years away, with a mass roughly comparable to Earth's. For a brief moment, it was the most discussed planet outside our solar system. Then the debates began. Other teams could not confirm the signal. Some analyses suggested the detection might be a stellar artifact, a pattern produced by the star itself rather than by any orbiting body. Its status remains uncertain. It may exist, it may not. It was the first name many people learned, and it may never be confirmed. 4 light-years closer, Gliese 832c is more secure. A super-Earth with roughly 5 times Earth's mass, confirmed in 2014, orbiting its M-dwarf host in about 36 days. It sits inside the habitable zone. It is probably tidally locked. Its host star is only 16 light-years away, which puts it among the nearest confirmed habitable zone candidates. It receives enough stellar flux to allow liquid water under the right atmospheric conditions. Whether those conditions exist, no one yet knows. Then the Kepler catalogue opens, and the list deepens considerably. Kepler 4422b sits 1,190 light-years from Earth. Its host is a K-type star, slightly cooler and calmer than the Sun. The planet's radius is about 1.3 times Earth's, small enough to suggest a rocky composition is at least possible. It completes one orbit every 240 days, a period not entirely unlike our own year. Its Earth Similarity Index score is roughly 0.83 out of a possible 1.0. That is one of the highest scores in the confirmed catalogue. It is, by most measures, one of the better rocky habitable zone candidates the Kepler mission produced. Kepler 438b was announced at the same press conference in January 2015. Its radius is about 1.1 times Earth's, even closer to Earth's size than Kepler 442b. It orbits an M-dwarf host 470 light-years away in about 35 days. But the reality was different. Follow-up analysis revealed that Kepler 438b's host star is moderately active. Not violently active, but enough. Some studies suggest the planet has likely experienced significant atmospheric stripping over its lifetime. A planet the right size, at the right distance, receiving radiation powerful enough to dismantle whatever atmosphere formed there. Not a guarantee of sterility, but a complication that the size and orbit alone do not reveal. The list continues. Kepler 1130b, 550 light-years away, roughly 1.66 Earth radii, orbiting a Sun-like G-type star. Kepler 1174b, 790 light-years away, about 1.5 Earth radii, orbiting a K-type host. That host star is approximately 7.5 billion years old, more than 3 billion years older than our own Sun. Whatever is happening on any world in that system has had an enormous amount of time to develop. Kepler 1283c, 640 light-years away, about 1.8 Earth radii, K-type host. Kepler 1410b, roughly 1,600 light-years out, similarly sized, orbiting an early M-dwarf in about 60 days. The names accumulate. Kepler 1638b, Kepler 460b, Kepler 1544b, Kepler 1649b, Kepler 1538b, Kepler 939c. The Kepler mission produced roughly 50 named planets meeting basic, habitable zone candidacy criteria. Most orbit M-dwarfs, with all the standard complications that implies. A smaller fraction orbit K or G-type hosts, where the stellar environment is calmer and the prospects for long-term atmospheric survival are meaningfully better. Most of these names will never become household words. Most will exist in the catalogue, quietly, with a radius and a period, and a host star classification, until instruments capable of reading their atmospheres come online. Each one is a real place. Each one is tracing its orbit tonight around its own star, indifferent to whether anyone has looked at it long enough to understand it. While Kepler looked far, the TESS mission began building the nearby catalogue. TOI 700d is 101 light-years from Earth. Its radius is approximately 1 Earth radius, making it one of the most Earth-sized confirmed habitable zone planets in the catalogue. It orbits an M-dwarf. All the standard questions apply. TOI 2285b is closer, only 42 light-years away, a candidate habitable zone world orbiting a K-dwarf, which makes its host considerably calmer than most of the M-dwarf entries. TOI 1906b and TOI 2576b and others are scattered through the nearby catalogue, each within a few hundred light-years, each still under follow-up, each carrying an uncertain status that will resolve over the coming years. But the genuinely close systems are worth pausing on. Barnard's star is 6 light-years away, the second closest stellar system to the Sun. An old, very quiet M-dwarf, with one of the lowest observed flare rates among our nearest stellar neighbours. It is, by that measure, one of the more habitability-friendly M-dwarfs in the immediate vicinity. In 2018, a candidate planet was announced, Barnard's Star B, a super-Earth in a long orbit near the outer edge of the habitable zone. The detection was later disputed. Some teams could not reproduce the signal. More recent observations have pointed toward a different, smaller, hotter planet on a tighter orbit, well inside the habitable zone boundaries. Its status remains genuinely unresolved. What is not disputed is that Barnard's Star is a prime target for future direct imaging. If any planet is there, instruments coming in the next decade should see it. Lalande 21185 is 8.3 light-years from Earth, the fourth closest star to our Sun, another quiet M-dwarf. A tentative candidate planet has been identified at the inner edge of its habitable zone, carrying a mass of roughly 3 times Earth's. It is probably tidally locked. The detection is not yet robust, but the system is close enough that continued observation will either confirm or retire the candidate in the foreseeable future. Beyond the named catalogue, there is the statistical population. Kepler's survey established that rocky, habitable zone planets are common. Within 50 light-years of Earth, the numbers suggest there should be dozens of M-dwarf habitable zone rocky worlds and several around K and G-type hosts that have not yet been detected. Not because they do not exist, because current methods favour shorter orbital periods, and habitable zone planets around quieter stars tend to have longer ones. They are sitting beyond the detection threshold of techniques calibrated for closer, faster orbits. The next decade of TESS observations and radial velocity refinements will bring most of them into the named catalogue. By the late 2030s, the expected list of named habitable zone candidates within 50 light-years is projected to contain several dozen entries. And so the catalogue grows, entry by entry, name by catalogue name. Kepler numbers and TOI numbers and Gliese numbers, each one attached to a real specific world following its own path through its own sky. Most will never be famous. Most will spend decades as a line in a table, a radius, a period, a flag for habitability, a note that further observations are warranted. But the length of that list is not a footnote. It is the finding. The universe did not produce 1 or 2 places that might be right. It produced dozens within our observational reach, and statistically many more just beyond it. And that reality holds whether any single entry in the catalogue turns out to be inhabited or not. The list is patient, and the next generation of instruments will read it far more carefully than we have been able to. That list keeps growing. And the question it raises is not small. If dozens of candidates exist within our direct observational reach, how many exist beyond it? How many worlds fit the basic description of a potentially habitable place, not just in our stellar neighborhood, not just in our galaxy, but everywhere? The named catalogue gives us a starting point. Roughly 50 to 60 planets currently carry basic habitable zone candidacy status, and enough characterization to be discussed as specific worlds. That is the floor of direct knowledge. It is not the ceiling, not even close. To estimate the full population, astronomers work from a single central statistic. It is called Eta Earth. Written with a Greek symbol, pronounced exactly as it sounds, it means one thing: the average number of Earth-sized planets in the habitable zone per Sun-like star. One number, one ratio. And from that ratio, an entire population can be extrapolated. Here is what the current data says. The modern best estimate for Eta Earth clusters between roughly 0.3 and 0.8. That range comes from multiple independent analyses of the Kepler mission dataset. The most widely cited current figure comes from a NASA analysis published in 2021, using the complete Kepler dataset rather than earlier partial samples. That analysis places Eta Earth at approximately 0.5 for Sun-like stars. Roughly half of all Sun-like stars appear to host at least one Earth-sized planet in their habitable zone. At the conservative end, the estimate drops as low as 0.1, meaning perhaps 1 in 10. At the optimistic end, it reaches 0.8, meaning roughly 4 out of 5. The honest answer lives somewhere in that range. The exact value is not yet known. Now comes the multiplication. The Milky Way contains approximately 400 billion stars. About 10% of those are G-type stars, the classification that includes our own Sun. That gives roughly 40 billion G-type Sun-like stars as a strict baseline. multiply by eta Earth at the midpoint value of 0.5, and the result is approximately 20 billion Earth-sized habitable zone planets around Sun-like stars in our galaxy alone. Then, the pattern broke. That 20 billion figure uses the strictest possible definition of Sun-like. If the definition expands to include K-type stars, the slightly smaller and cooler but still stable long-lived class that makes up a larger fraction of the galaxy, and the quietest M-dwarfs that orbit without stripping their planets bare, the number climbs into the hundreds of billions. A reasonable headline figure, using a broadened but still conservative definition, lands near 40 billion Earth-sized habitable zone worlds in the Milky Way. The honest range runs from about 2 billion at the pessimistic extreme to roughly 100 billion at the optimistic end. And that is before adding anything beyond surface water rocky worlds. Before Hycean candidates. Before icy moon subsurface oceans. Before rogue planets with their internal heat and thick insulating atmospheres. The full count of plausibly habitable places in the Milky Way, using every reasonable category explored in recent decades, maybe several hundred billion or beyond. The numbers stop translating into felt sense, somewhere around here. And then, the scale expands again. The observable universe contains somewhere between 200 billion and 2 trillion galaxies. Recent deep field observations from the James Webb Space Telescope have revised some earlier estimates, but the range remains staggering. The Milky Way is relatively large by galactic standards. If the average galaxy hosts a somewhat smaller habitable population, the universe scale total still arrives at somewhere between 1 quintillion and 10 sextillion Earth-similar habitable zone worlds. 1 quintillion is a billion billions. 10 sextillion is 10 times a billion billions. Repeated again. There is no household object to hold that comparison. The numbers are no longer numbers in any felt sense. They are a category of magnitude. By every reasonable extrapolation, the universe contains an essentially uncountable habitable population. A formal structure for thinking through this kind of multiplication has existed since 1961. The astronomer Frank Drake proposed it at a small scientific conference, writing it on a blackboard as a way to organize a conversation about how many communicating civilizations might exist in the galaxy. The equation bears his name. It has 7 factors: the rate of star formation in the galaxy, the fraction of those stars that form planets, the average number of habitable planets per planetary system, the fraction of habitable worlds on which life actually arises, the fraction of those on which intelligence develops, the fraction of those that develop technology capable of signaling across space, and finally, the average lifetime of such civilizations before they go silent. Multiply those 7 factors together, and you get an estimate of how many communicating civilizations exist in the Milky Way right now. For most of the 6 decades since Drake wrote that equation on a blackboard, nearly every factor was unknown. The best scientists could do was substitute guesses. The equation organized the ignorance without resolving it. That has changed. Not for all 7 factors, but for the first 3. The rate of star formation in the Milky Way is now well measured. Several new stars form each year. The fraction of stars that host planets is no longer a mystery. It is essentially 1. Survey after survey from Kepler and TESS and radial velocity programs has converged on the same finding. Planets are ubiquitous. Nearly every star hosts them. And eta Earth, the average number of habitable planets per star, has been narrowed to somewhere between 0.1 and 0.8. Still a wide range. But it is a range, not an open question. The first half of the Drake equation has been substantially answered. 3 of the 7 factors now carry real numbers rather than blank spaces. The second half has not. The fraction of habitable worlds on which life arises, the probability of abiogenesis, the step from chemistry to biology, is unknown by many orders of magnitude. We have exactly 1 data point, Earth, and 1 data point cannot anchor a probability. The fraction of life-bearing worlds on which intelligence develops is equally unconstrained. The fraction that build communicating technology, and especially the average lifetime of civilizations before they go silent, may be the most uncertain number in science. Wait, the Drake equation is sometimes discussed as if it is a calculation. It is not. It is a structure for organizing ignorance. It does not produce answers. It maps what we know and what we do not. The first 3 factors are now real entries. The last 4 remain open by orders of magnitude. That distinction matters. It also means this: when anyone says the Milky Way contains tens of billions of habitable worlds, that claim carries embedded assumptions worth naming. If the conservative habitable zone definition is correct, if E-to-Earth holds in the current range, if the broader habitability categories are not added, if architectural constraints like stellar flares and magnetic fields and plate tectonics do not eliminate most candidates, then tens of billions. Each of those conditions is itself uncertain. The order of magnitude is settled. The precision is not. The number is large, and that is what the data supports. The exact value is something the next decade of instruments will narrow considerably. The Habitable Worlds Observatory, currently in development for launch in the late 2030s or early 2040s, is designed specifically to image Earth analog planets around nearby sun-like stars and measure their atmospheric compositions. The Roman Space Telescope's microlensing survey will sample the galactic population of planets in orbital configurations Kepler could not reach. Together, these 2 programs should substantially tighten the E-to-Earth estimate and reduce the uncertainty range by a significant margin. By the early 2040s, the population estimate may be much more precise than it is today. For now, the summary is this: the Milky Way contains somewhere between several billion and several hundred billion plausibly habitable worlds. The observable universe contains somewhere between 1 quintillion and 10 sextillion. The number is large. The exact value is not yet known. Whether any of those worlds are inhabited is entirely open, and the structure of the question has only recently become clear enough to answer rigorously. The first 3 factors have been filled in. The rest of the equation is still waiting. And the waiting is not passive. It points directly at the most important question, underneath all the counting. The number is real, but a habitable world is not the same as an inhabited world. And the distance between those 2 things is the size of everything we don't know. A habitable world has the right address, the right distance from its star, liquid water in principle, an orbit that holds, but something else has to happen next. Chemistry has to organize itself into something alive, and we have no idea how often that happens. This is where the conditional probabilities begin. There are 4 of them. Each one multiplies into the next, and each one is currently unknown by many orders of magnitude. Together they determine what fraction of all those plausible, habitable worlds are actually inhabited by anything that could signal its presence across space. The product of all 4 could be close to 1, or it could be 1 in a billion. The data cannot yet say. The first probability is biogenesis. Given a world with the right architecture, the right chemistry, the right energy gradients, what fraction actually generate life? We have one example: Earth. On Earth, life arose within perhaps a few 100 million years of the planet becoming habitable. That sounds fast on geological scales. Some researchers take it as a sign that biogenesis is not vanishingly rare. Others argue that because we are asking the question from inside a life-bearing world, we are looking at a sample that is guaranteed to have succeeded. We cannot see the planets where chemistry organized for a billion years and stopped short. One example tells us the probability is not 0. It tells us nothing more than that. The second probability is harder, and here is where the chain first shows signs of being genuinely narrow. Life on Earth arose quickly, but complex life did not. The first cells were prokaryotes, simple organisms without a nucleus. They dominated this planet for roughly 2 billion years. Then, approximately 2 billion years after life first appeared, a transition occurred that appears to have happened only once in Earth's entire history. A prokaryote cell engulfed another, and instead of destroying it, incorporated it. The incorporated cell became what we now call the mitochondrion, the energy-producing structure inside nearly every complex cell. This transition produced the eukaryote. The eukaryote made complex multicellular life possible. That transition appears to have happened exactly once. Not multiple times, not in parallel lineages. Once. Every complex organism on Earth, every animal, every plant, every fungus, traces back to that single improbable event. Whether the eukaryotic transition is a universal step that happens wherever life arises, or a freak accident that happened to occur here and shapes everything that followed, is one of the deepest open questions in all of biology. It is the leading candidate for what some researchers call a bottleneck step, a place in the chain where the probability drops sharply. The third probability follows. Complex multicellular life has existed on Earth for roughly 600 million years. Recognizably intelligent animals, creatures with tool use, social learning, and complex problem solving have existed for at most a few tens of millions of years. Human-level intelligence, the kind built on language, symbolic thought, and cumulative cultural learning where each generation inherits the knowledge of the last, has existed for perhaps a few 100,000 years. 600 million years of complex life. A few 100,000 years of anything resembling us. The fourth probability is the narrowest window of all. Technologically capable civilization has existed for at most a few thousand years. A civilization capable of emitting radio signals detectable across interstellar distances has existed for about 1 century, 100 years, against a planet 4.5 billion years old. The window in which any civilization is detectable from outside its own solar system may be very short, at least so far. Multiply those 4 probabilities together, and you arrive at the fraction of habitable worlds hosting a civilization that could be detected right now. The product could be nearly 1, or it could be 1 in a billion. Estimates from serious researchers span that entire range. This is not a failure of the science. It is an honest description of how little information 4 data points anchored to a single example can provide. 2 scientifically respectable positions have emerged from that uncertainty. The first is sometimes called the Copernican position. It holds that Earth is roughly typical. Life arose here quickly, suggesting biogenesis is not catastrophically bottlenecked. The conditional probabilities, while individually small, multiply to something large enough that a galaxy with tens of billions of habitable worlds should contain millions or billions of inhabited ones, and many with technological civilizations. The second is the rare Earth hypothesis. It holds that the chain is extraordinarily narrow, not because any single condition is impossible, but because of the conjunction. Consider what Earth actually required. A host star of the right type, neither too small, nor too large, nor too active. A position inside the galactic habitable zone, the narrow ring of the galaxy with sufficient heavy elements, but low enough radiation density. A protective architecture of outer giant planets to absorb or deflect incoming impactors. A planet of the right size, the right orbit, the right chemical composition. A magnetic field generated by an active iron core. Plate tectonics to regulate the carbon cycle over billions of years. A large stabilizing moon to hold the axial tilt constant. A long-lived atmosphere. Persistent oceans. A stable rotational axis. A low ongoing impact rate. A stable orbital configuration across billions of years. And enough time for all of it to compound. Every one of those conditions is plausible in isolation. The conjunction of all of them, held simultaneously, for the billions of years that complex life requires, may be very rare. The picture did not hold. The rare Earth argument and the Copernican argument are both consistent with the current evidence. Neither has been ruled out. We don't have a representative sample. We have one example of a life-bearing world. That example tells us the conditional probabilities are not zero. It cannot tell us how small they are. But the next decade will begin to narrow this. The Habitable Worlds Observatory is designed specifically to image Earth analog planets around nearby sun-like stars and measure their atmospheric compositions. If even one nearby habitable zone world shows clear biosignatures, gases present at abundances that chemistry alone cannot easily explain, the rare Earth position becomes much harder to sustain. If the first several dozen habitable zone worlds all come back lifeless, the rare Earth position becomes much more plausible. The great filter sits underneath all of this. The idea is simple and uncomfortable. Somewhere along the chain from habitable world to communicating civilization, at least one step must be fantastically improbable. Improbable enough to explain why we have not detected other civilizations despite the high frequency of habitable worlds. That improbable step is the filter. The filter could be behind us. If the bottleneck is the rise of complex life, the eukaryotic transition, or the development of intelligence, then we have already passed through the most difficult step. The rest of the road, if it exists, may be relatively open. The filter could be ahead of us. If the long-term survival of technological civilization is the bottleneck, the difficulty of persisting across the timescales required to be detectable across interstellar space, then we have not yet reached the most dangerous part of the chain. We may be approaching it. Which one it is, we currently do not know, and then there is the silence itself. Several decades of radio searches, optical laser surveys, and waste heat infrared scans have produced no confirmed evidence of any technological civilization anywhere in the galaxy. No signal, no structured emission, no anomalous infrared excess attributable to large-scale engineering. Nothing that requires another intelligence to explain. The silence is real. It carries information. It is consistent with at least 4 explanations. We may be alone. We may be too early, with most civilizations still in the future. Civilizations may be quiet by design, having moved beyond broadcast technologies we would recognize. We may not yet be listening correctly, scanning the wrong frequencies or the wrong fractions of sky. The silence does not yet distinguish between these possibilities. What it tells us is this: the catalogue of habitable worlds is real. The catalogue of inhabited worlds beyond Earth remains, for now, empty. The gap between those two catalogues is the size of the conditional probabilities multiplied by the silence, divided by whatever fraction of any signal we are currently capable of detecting. That gap contains one of the most important unknowns in modern science. The headline number, somewhere between billions and sextillions of plausibly habitable worlds, remains true. The inhabited number remains, for now, 1. And whether that will change depends on evidence we are only beginning to know how to gather. And gathering it is already underway. James Webb Space Telescope has been operating since mid-2022. In its first few years, it produced the most detailed atmospheric characterizations ever obtained for habitable zone candidates. Some of those results surprised the field. The inner planets of the TRAPPIST-1 system showed no detectable thick atmospheres. Their dayside temperatures were consistent with bare rocky surfaces, stripped by billions of years of stellar irradiation. That softened expectations for ultra-cool dwarf worlds close to their stars. But then came K2-18b, methane, carbon dioxide, the tentative whisper of dimethyl sulfide. That result raised expectations for an entirely different kind of world. Not a rocky surface under an open sky, a hydrogen-wrapped ocean planet where biology, if it exists, would look nothing like what we know from Earth. 2 results, pointing in 2 different directions, sharpening 2 different questions. By the late 2020s, the field will have atmospheric measurements on dozens more candidates, and the picture will be much more clearly defined. The Roman Space Telescope follows, scheduled for late this decade. Its primary tool is microlensing, a technique that watches for the gravitational bending of distant starlight as a planet passes between its star and our telescopes. Where Kepler found close-in worlds in short orbits, Roman will find cold, distant, and free-floating worlds that transit surveys cannot reach. Thousands of new exoplanets are expected. The population statistics for habitable zone worlds at longer orbital periods will sharpen considerably. E to Earth, the average number of Earth-sized habitable zone planets per Sun-like star, currently sits in a range from roughly 1 in 10 to 4 in 5. Roman is expected to narrow that range substantially. The rogue planet population will also be characterized in detail for the first time. How many starless worlds drift through the galaxy, warm inside from radioactive decay, possibly harboring subsurface oceans under thick atmospheric blankets, will become an observationally constrained number rather than a statistical estimate. On the ground, 3 enormous telescopes are under construction and expected to begin operations in the late 2020s and early 2030s. The extremely large telescope in Chile will carry a 39-meter primary mirror, roughly the width of a 10-story building laid on its side. The giant Magellan telescope, also in Chile, uses 7 mirrors each 8.4 meters across, arranged as a single optical system. The 30-meter telescope in Hawaii will carry a 30-meter primary. Each of these instruments will be capable of directly imaging planets around the nearest stars and measuring their atmospheric compositions through spectroscopy. If Proxima b has a thin remnant atmosphere, these telescopes may characterize it. If any of the nearest known habitable zone candidates carries biosignature gases, there is a strong chance these instruments will find them. The nearest stars are no longer out of reach. They are about to become addressable questions. Further out on the timeline sits the instrument the field has been building toward for decades. The Habitable Worlds Observatory, a NASA flagship in concept development, is projected for launch in the early to mid-2040s. Its specific design goal is to directly image at least 25 Earth analog planets around nearby Sun-like stars and obtain spectroscopic atmospheric characterizations of each one. Not transits, not indirect signals, direct images, actual photons from the surfaces of Earth-sized worlds dispersed into spectra and searched for oxygen, water vapor, methane, carbon dioxide, and the chemical combinations that would be difficult to explain without biology. If it flies on schedule and meets its specifications, the question of whether any of the nearest 25 Sun-like stars hosts a planet with the chemical signatures of life will be substantially answered within roughly 20 years of its launch. Other instruments fill in the gaps. Plato, an ESA mission scheduled for the late 2020s, will conduct long-duration transit surveys of bright Sun-like stars, searching for Earth analogues with orbital periods measured in months to years, the kind of planet most likely to have conditions similar to our own. Ariel, also from ESA, will characterize the atmospheres of hundreds of planets across a wide range of temperatures. Ground-based programs including Espresso at the Very Large Telescope, Maroon X at Gemini North, and Express at the Lowell Discovery Telescope are pushing radial velocity precision into the range where Earth-mass planets become detectable. Beyond those, the concepts become more speculative. Space-based interferometers capable of resolving surface features on nearby Earth analogues. Solar gravitational lens focal missions that could, in principle, produce high-resolution images of exoplanet surfaces by using the Sun's own gravity as a focusing element. These are not funded missions. They are trajectory. They describe what the second half of this century may become capable of. But here's where the picture gets harder. All of those instruments, from Roman to the Habitable Worlds Observatory to the most ambitious concepts of the 2060s, share one constraint. They observe remotely. They read out atmospheres and surfaces across light years. They do not visit. Wait. The fastest spacecraft humanity has ever launched is the Parker Solar Probe, which reached a peak speed of roughly 150 kilometers per second during close solar passes. That number sounds fast. At that speed, the journey to Proxima Centauri b, the nearest known potentially habitable world at 4.24 light-years, would take approximately 8,500 years. Not a long mission, not a challenge of engineering, a span of time longer than all of recorded human history. Not a probe we can send this century, not in the next several. Concepts exist. Breakthrough Starshot proposes laser-pushed light sails carrying gram-scale probes toward Alpha Centauri on a roughly 20-year journey. The physics is real. The engineering does not yet exist. If the project launches at all, mid-century is the earliest plausible window, and the probes would be cameras and sensors, not landers. For the foreseeable future, the answers to the habitable zone question will arrive the way all exoplanet answers arrive. Spectroscopy, photons crossing light years, a remote reading of what chemistry exists in atmospheres we will never breathe. The first confirmed biosignature on any exoplanet, if it comes, will be something like what the first confirmed exoplanet itself was in the mid-1990s. A turning point, a moment when the question shifts from whether to which, and from which to how many. Whether that confirmation arrives in 2030 or 2040 or 2050 or never is what the next several decades will answer. The honest answer to the larger question is layered. It always was. The first layer is certain. There is exactly one confirmed inhabited world. Earth. One example. One calibration point. The only planet from which the question has ever been asked. The second layer contains dozens of named places. Kepler 22b at 620 light-years, the first habitable zone world confirmed around a sun-like star, possibly an ocean planet, possibly a gas-shrouded mini-Neptune. its composition still unknown. Kepler 452b at 1,400 light-years, slightly older than Earth, orbiting a slightly brighter star, sitting near the inner edge of its habitable zone, where a runaway greenhouse may already be underway or may be approaching. Proxima b at 424 light-years, the nearest known candidate, perhaps a Terminator Twilight world where permanent day meets permanent night, along a ring of perpetual dusk, perhaps a stripped, airless surface, we do not yet know. The 7 resonant worlds of TRAPPIST-1 at 39.6 light-years, 3 of them in the habitable zone, orbiting a star that will still be burning long after the sun has become a cold remnant. K2-18b at 124 light-years, a hydrogen-skied ocean world with methane and carbon dioxide, and the faint possible trace of an organic compound that almost nothing but marine biology produces on Earth. Kepler 186f, Kepler 1649c, and behind them, dozens more in the quiet background catalogue, known mostly by transit depth and orbital period, each a real specific world orbiting its own star tonight. The third layer translates into numbers, but not into feeling. Somewhere between a few billion and a few hundred billion plausibly habitable, Earth-similar worlds in this galaxy. Somewhere between 1 quintillion and 10 sextillion across the observable universe. These are not errors in the math. They are the math. The universe is simply that large. The central unknown is not how many habitable worlds exist. That question is answered. Many. The central unknown is how many of those worlds are actually inhabited. What the silence in our radio telescopes is telling us, whether the chemistry of life assembles itself readily wherever conditions allow, or whether it happened here by a conjunction of events so unlikely that the rest of the galaxy is, for all practical purposes, empty, whether the quiet is emptiness or just distance and time. The first reframe is this: a galaxy with tens of billions of habitable worlds, and only one inhabited world is, in a real sense, almost as quiet as a galaxy with only one habitable world, and one inhabited world. The headline number, the tens of billions, does not by itself populate the sky with company. Habitable and inhabited are different catalogues. Only one of them has more than one entry. The second reframe is this: even if the inhabited count is small, the habitable count remains real. Tens of billions of worlds in this galaxy alone where liquid water could exist, where temperatures fall within the range biology as we know it requires, where atmospheres might persist long enough for chemistry to run its long experiments. Each one is a place the universe has prepared for the possibility of life. The preparation is real even when unused. The oceans turn beneath atmospheres that never produce anything to swim in them. The Terminator rings of tidally locked planets stay in permanent twilight, dim red stars fixed at the horizon, without anyone walking under that sky. The chemistry sits ready. Most of the time, it sits ready forever. The third reframe is quieter still. The question of how many habitable worlds exist is also, under the surface, a question about what habitable means. The conservative definition, liquid water on a solid surface at roughly Earth normal pressure, produces one count. The optimistic definition, extending the edges of the zone based on what Venus and Mars tell us the range could plausibly reach, produces a larger one. The Hycean definition, sub-Neptune ocean worlds insulated by thick hydrogen atmospheres, produces a different count again. The subsurface ocean definition, icy moons and rogue planets warmed by internal heat, with no star required at all, produces a larger count still. The answer shifts with the definition. But the answer is large by every version of the question. That part does not change. Somewhere in Cygnus tonight, a possibly oceanic world traces its 290-day orbit, around a star slightly cooler than ours. Somewhere in Centaurus tonight, a small rocky world sits locked into permanent day and permanent night, around the dim red dwarf nearest to us. Somewhere in Aquarius tonight, 7 Earth-sized worlds resonate in orbital harmony around an ultra-cool dwarf that will still be burning long after everything we can see in tonight's sky has gone cold and dark. Somewhere in Leo tonight, a hydrogen-skied ocean planet turns slowly, its atmosphere carrying the faint chemistry of methane and carbon dioxide, and perhaps the soft trace of an organic compound we cannot yet confirm. Each of those places is real. None will be visited in our lifetime. Most will never be visited at all. All of them are there, orbiting, turning, indifferent to the question we are asking about them. There are many habitable planets out there. The galaxy is full of plausible homes. The universe is fuller still. Most are dark. Most are silent. Most will never tell us whether anything is alive in them. A few may begin to answer in the next several decades. Until then, the question lives where it has always lived, between one confirmed world and tens of billions of plausible ones, between the silence we hear tonight and the answers we may have within 30 years. The galaxy is large enough that the answer is almost certainly not zero. It is patient enough to keep its other lit windows hidden a while longer.